Fold mountains. Pretty sure this is where we are. We just want to confirm. I gave an introduction of mountains, then we just ended with fold mountains because fault block mountains require discussion. Right, thanks for the response. Thank you. So today's lesson plan will continue from here. So we have started mountains. Okay, under mountains we have seen only first type, fold. So today we will finish geomorphology. We'll go to fault block mountains. After fault block mountains, we'll just need to discuss one more point regarding fold mountains. Not just fold mountains, generally regarding mountain building. Like even after the fault block mountains are over, you will feel that there is a minor problem with theory. So we'll just see how plate tectonics tackle this problem. Okay, if that is done, then we have earthquakes. See, earthquakes will not be surprising. The reason is you've already finished the basics of seismology. You know, what are primary waves, what are secondary waves, and what are tertiary waves, or the surface waves. So if you've learned volcanoes and mountain building, earthquakes are not going to take much time at all. We'll understand the fundamentals with reference to natural factors. Anthropogenic factors will take some time. Then we have an isolated segment called as isostasy. Isostasy will be relatively new. It's a mains topic, but still, it should not take more than 30-40. And then finally, basics of erosion, weathering, and mass busting. And then I'll tell you how to work on this particular part. Okay, this is the first part of the class. So geomorphology, we will wrap it up possibly in 1 hour or 1 hour 5 minutes. So second section will be oceans. As I told in the previous session, isn't it? So this is the last part of a class. So under oceanography, today we'll be looking at marine provinces, the broad divisions under the ocean floor. And after marine provinces, we look at characteristics of ocean salinity. So starting from, why is the ocean salty, and what are the factors which will affect ocean salinity? Why certain parts of the world have more salt content compared to the others? So that we'll discuss. Then we need to look at variation part. I mean, how does your salinity vary with reference to latitude and depth? Ocean salinity will not be same. If you stay at the top surface of water and let's say you dive down 500 meters or 1500 meters, it'll be different. Or you take your ocean temperature. Ocean temperature is not going to be same at the surface level and the bottom level. So how does things vary? Then finally, ocean water density variations. Is it clear? And after finishing this, if time permits, we don't know. Like if time permits, I will start with waves. Okay. So that's the lesson plan for today. I believe the issue is settled. Now let me start with the concept which we couldn't finish last class. Fault block mountains. Fault block mountains. I'll give the definition, then I'll explain. Fault block mountains. See, fold mountains were very simple. You just had this compression, then you created a wave-like bend, right? So that is your fold mountain. You take fault block mountains, we need to establish some definitions at the start. What is faulting, of course? Okay, then from faulting, we will derive some divisions, what is called as normal fault, reverse fault, dip, slip, certain terminologies. Then we'll go to fault block. Ready for this? Okay. A fault is a fracture on the earth crust. Fault is a fracture on the earth crust. Along which crustal blocks can move. Crustal blocks can move. Full stop. Simple definition. Fault. Read it one more time, then I'll explain in detail. A fault is a fracture on the Earth's crust along which crustal blocks can move. Okay. See, if you've ever cut cakes for your birthday, then understanding faulting is way too simple. Okay, maybe the last time you did it was in your college. Or maybe if someone is there in college, then you might have experienced that. Once the college is over, that's it. School and college time is the only time when you do that. After that, no one really cares about you anymore. Okay, now talking about fault block landscape. Let's say this is your cake and it's your birthday. You're about to cut it. Now, when you cut it, what you exactly do is you create vertical fractures. Is it not? So what you do is you make a cut here and make a cut here, then one vertical line here, one vertical line here, then tada, it's ready. You'll eat it. Now, once they've isolated the structure, see what happens. They're not the same cake. So the cake is not perfect. Cake is right there. The segment is cut. And it works like this, right? Now, this individual yellow color piece, which you've taken, maybe butterscotch flavor, can be moved up and down. Is it not? Now, you can take this out. There is absolutely no problem at all. See, this is technically faulting. See, you take the Earth's crust's composition is not the same everywhere. Certain parts of the crust will be stronger, certain parts will be weaker. So, wherever you find those weak lines, you will develop fractures. Now, you might be asking, why are we developing these fractures? See, the primary reason being the convective currents are quite strong. What is happening inside the Earth? We've established your relationship with reference to your volcanoes. So you know that there are certain parts of the world where your convective currents are stronger and certain parts where convective currents are weaker. And your plates are constantly moving. So because of that, there is collision in certain areas, there is movement away from certain areas. That will create fractures. Got it? So these we are talking about vertical divisions. If this is going to be my Earth's crust, entire crust, the crust is broken vertically. You get the meaning what exactly is a fault. So fault is a fracture on the Earth's crust along which crustal blocks can move. So if a segment is isolated because of a fracture, this block can either move up or either move down. And that can create landforms like mountains. Meaning makes sense. So this is the meaning of fault. Now two more definitions associated with that. Dip, slip, normal fault and reverse fault. Is it clear? Just a second. Right, moving on. Believe you had enough time to copy this. So first we'll establish normal fault and reverse fault. Okay, let's say there are two blocks. Block 1 and block 2. Okay. Then two more here. Maybe I'll draw this. Only due to lack of space, I'll possibly draw it here. Okay. And this is on top. Right? Okay. So what exactly is a normal fault? And what is a reverse fault? Reverse. Also called as thrust fault. Compressional force. Take this diagram. Once you've taken the diagram, use the word finished. Let me explain. Okay. Take it down. Then let me see and let me tell you how your fault is supposed to work. What is the basic difference between normal and reverse fault? We'll understand with an example. See, I will get you pictures, but pictures come at the last session. Once the topic is over, then we'll look at pictures. Because I want you to imagine first. Then we'll see the actual landscape. Normal faults, tensional force, reverse fault, compressional force. Until you see the pictures, the exact visuals will be difficult, but try to do it. Use the word finish if you're ready. As things progress, you get it better. One response. Right, thank you. Now, see, I know it's highly uneven. Okay, but technically I should be for getting two notebooks of the same size. But under Earth conditions, you won't get the blocks of the same size. So let's say this is what I'm talking about, fractures. So one is a book and one is a notebook, and between them you see a line, isn't it? That is technically a fault or a fracture. Now see here, once you got two blocks, okay, these two blocks can move along the fault plane. The line is a fault plane, so this book can move either up or either down. So how do you classify a normal fault and reverse fault? It's technically based on the force which is acting. Look at both these pictures. If you think about this, these two pictures are not really different. I mean, really different meaning, yes, one person is going up and one person is going down. It is reverse in both the cases. But the point is, if you just observe it, you're not going to get the clear idea. One block stays up, one block stays up, one block stays down, one block stays down. Okay, but who stays down is what makes the difference. See, understand, the derivative is the force as such. Once the fault plane is created, possibly because of a weakness on the earth, let's say apply tensional force. Tension is you try to pull things apart. Pay attention. You try to pull things apart slowly but steadily. Okay, one person is going to slide down, right? See, my hands are actually moving away like this. But thing is, you can't separate like this. That is not possible. Okay, even though the forces are strong, it's not as strong as that. So what happens is, you just try to expand the force right here, and one block slowly slides out. Okay, so one block is falling. So this is the falling block. Got it? And this person is remaining stable, possibly because of better strength and structural integrity, slowly. Reverse is also possible. It's also called as reverse fold or thrust fold. Now, instead of tension, what you do is apply compression force. See what happens? Now you're applying it towards it. Now, when you do that, after a point of time, slowly but steadily, this book is going to rise up. Meaning makes sense. So during a thrust fault, the block which usually falls down moves up. So that's why I told you, by physical experience, you just look at an area, it's very difficult to conceive whether it is actually a hanging wall or a footwall which is going down. But technically, it is done by which force is dominant. Whenever tensional forces are dominant, you'll get a normal fault, okay, like this. And your compressional force is dominant, you'll get a thrust fault. Meaning makes sense. Now, next two set of words, dip and slip. See, it might seem technical, the next two terms which I tell you, but I'm introducing that because you need to learn tsunamis and oceans. That is why. Ready for that? Dip and slip. So, what is dip and what is slip? Simple enough. See, this diagram which you have written in your notebook, which you have drawn in your notebook right now, is very ideal. Very ideal meaning you got a perfect perpendicular block, right? These things won't be there in nature in most cases. Most of the time, they'll be inclined. One will be tilted, one will be broken, one will be siding at an angle and all that. So based on this, you just need to know two terms around. What is dip and what is slip? Got it? So it's an imaginary horizontal line or horizontal plane. Got the idea? So first, let's establish what exactly is this theta. See, this theta is called as dip. This one. DIP, dip. That's all. Remember this vertical, dipping. When you say I'm dipping down, you're falling down, right? So dip is the angle. Made by the rock bed with the horizontal. Number two, simple definition, strike. And this is strike. This one. Strike. Okay. Strike is the line formed by the intersection of the dip with the horizontal plane. Got it? Take it down. I will explain. See, if you think about this, we haven't started mountains at all. I'm just introducing certain terminologies. Okay? We will start soon. Next will be fault block landscape. Use the word finish if you're ready. The dip is the angle made by the rock bed with the horizontal. And strike is a line formed with the intersection of the dip with the horizontal plane. One response. I hope you're ready. Right, thank you. See, dip is very simple. See, a rock can have any angle. For example, the rock structure may be steep. The rock structure, I mean, if this is the, I think now we are seeing it very clearly. The rock structure may be very steep, maybe the angle is very high, or it is very, very gentle slope. You get the meaning? It can be very gentle also. So this is what you measure as your dip angle. Like, how is my rock actually tilting with reference to your surface? Okay, what is a strike is this. See, I measured my angle with reference to a horizontal plane. And you see that? If you need to measure your angle, you need a horizontal line. Okay, so this book serves as the line. Now, when I draw that horizontal line and superimpose it on the dip, see what happens? This is my actual rock structure. This is just an imaginary line. It doesn't exist in. This is my imaginary line. Both of them will intersect here, isn't it? Now, see this right now? This is called a strike. Got the idea? Dip is this vertical structure. This is dipping. See which side is which. Got it? So this is dipping. Pay attention again. This is dip angle. You see the book fall right now, dipping down. Okay. This is strike. This one. Now, why should you know the difference? Like, if you have a fault plane, you can have two different types of movement. Now, pay attention. Both the cases which we saw right now. This one. Both of them, it is dip type of movement. Dip-slip movement. Whenever someone uses the word dip-slip movement, it means the movement is along the vertical plane. Meaning makes sense. Either the book is slipping down or your false block is moving up. This is dip-slip movement. Able to understand the meaning? Dip-slip, dipping down. You go to the second one, you can also have false blocks moving along the horizontal. It is called a strike-slip movement. You can also have strike-slip. See, thing is, you might come across these terminology in textbooks. That's why. Strike-slip movement. Strike-slip movement is you move in this direction. You see that? Now, in strike-slip movement, there is no change in elevation. That's not the idea. But you definitely have friction. You get the difference? So that's the difference between your dip-slip movement and strike-slip movement. Both of them can actually cause friction. Both of them can create ruptures, definitely. This is the idea. Believe it was driven home. Shall I move forward? Use the word yes. You ready? Dip-slip is vertical and strike-slip is horizontal movement. Right now. Now we'll enter fault block landscape. We haven't talked about the mountains at all. So fault block landscape is one which is characterized by integrated and connected networks of hosts, grabens, half grabens, etc. You will learn what is host and graben in the next slide. Fault block landscape is one which is characterized by integrated and connected networks of hosts, grabens, half grabens, etc. So you go to an area like, or you might find all these. That is when you describe something called as a fault block landscape. In India, if you want to possibly view a fault block landscape, if you're already in a state in Maharashtra or Madhya Pradesh, you're actually in one. Okay, that's a very good place where you can see these. Maharashtra and Madhya Pradesh have quite extensive fault block landscape. See, in this fault block landscape, I'm going to explain how mountains or how exactly valleys and then your hills were actually formed. Is it clear? So if it's a very large area, I'm trying to present what will happen in a localized section. For example, in this isolated region, what exactly is happening? That is what we are going to conceive. See, and it's a very complex phenomenon which will go on in each and every domain. But if you can know what is happening in a small location, you can kind of interconnect and see what will expand over possibly tens of kilometers, possibly for a 60-kilometer length, or maybe for 60 square kilometers. What will be the landscape? That is the idea. So now we will establish, let's say you have a triple block structure. We'll take a small section. That if you've understood, you will know that how mountains and valleys are created. Okay, we'll take a very simple triple block structure and we'll understand how your mountains are formed. Ready? So a simple triple block structure How does it create host and graben? See, when I say triple block, we are increasing the number of falls. Let's say 2 falls. Simple. 1, 2, and 3. 3 books or 3 notebooks or 3 blocks. Okay. Now, let's say you have a tensional force. So I'd rather apply compressional force first. I explain thrust fault. Compressional force is there. Pay attention. Now, when you apply compressional force, narrow area, let's say compression is dominant, you'll get something like this. Okay, possibly a 2 stays down and 1 gets thrust over, a 3 gets thrust over. Okay, 3 and 1 stand as host and 2 stands as graben. Wait, understand this and write, because some of you might have difficulty in visuals. See this right now. 1, 2, and 3. Pay attention to me first. Then you can copy it down. Okay. This is block number 2, my face. Okay, this is block 1. This is block 3. Able to understand right now? I think I'm trying to position myself right there. 2 is my head, the book on, yeah, this is 3 and this is 1. Able to visualize it? So these are my fault planes, the separation point. Fault plane here and fault plane here. Got the idea? So what we're going to do right now is apply compressional force and see what happens. See, when you apply compressional force, okay, my face is not going to get jammed because my skull has a certain level of integrity, right? You can squeeze it, of course, but you really can't squeeze it. Like you can't make tomato juice out of that or blood juice, whatever it is. So this integrity is same for rocks also. Rocks are quite hard. It's not possible to just squeeze them and then make it liquid. Not possible at all, no juice. So once you start compressing, there will be some resistance. And one resistance is, see what happens? Compression, and happens over hundreds of years. Compression, 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 compression. Slowly you'll see that both the notebook and book are actually rising up. You see that? And this will happen over hundreds of years. So these two elevated structures are hold as host, 1 and 3. They move up. And my head, look at the location right now. My head stop, at the top of my head is at a lower position. Meaning makes sense that this one I'm talking right now. This will stay as a graben or a valley. Got it? So these two will remain as host. Take it down. Use the word finished if you're done. This is one example. Two responses, good. One more, I'll proceed. Right. See, this is the problem, you know. Where does the compressional force come from? See, I'll tell you now, listen very carefully. The compressional and tensional forces come from the convective currents which happen in the asthenosphere. It has been dealt with in volcanoes. See, please note, this is the problem. The forces are way too complex than you imagine. This is the crust. Everywhere convective currents will be operating. There will be convective currents here, convective currents. Maybe the crust moves like this. Maybe convective currents are here. It's way too complex. Maybe in one section there is... See, crust is over here and asthenosphere is everywhere. Don't visualize a very small section. Every part of the earth, certain areas will be hotter, certain areas will get colder. And blocks are actually getting thrust. See, it's like you're standing in the middle of the crowd and people are moving around you. One person will push you to the left, one person will push you to the right. Okay, please don't ask me that question, where does the force come from? Because in the previous session, I've dealt enough time in detail that asthenosphere has enough amount of radioactive elements, and radioactive elements provide enough heat for your plates to move. Last time I won that question on my chat box. Got it? Because the question comes later, after I finish plate tectonics, after I finish volcanoes, when we are almost about to finish mountain building, you ask that question, that's why. Now we'll talk about a second case. Then we'll see examples. Got it? 1, 2, 3. 1, 2, 3. 1 and 2. Okay. This time, rather than compression, I'll apply tension. 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 Or did we use... Okay, sorry. I'm again drawing the dragon for compression. Right? Tension. Tension. Now, I'm going to give you two options. Option 1 and option 2. You'll have to reply to me which will be the final result. Ready? Look at this. Option 1, I'll give you this. 2 stays up. 1 and 3 get pulled down. Or 1 and 3 stay up. 2 get pulled down. Two possibilities. You tell me one or two, which is true. Graben means valley. Yes, correct. 1, 1, 2, 1. Other music composition. Music composition. 1, 1, 1, 2. See, the answer is both. Is it clear? But please pay attention. Thing is, mostly this will happen. Mostly this will happen. Look what happens. See, very simple. Tensional force. My head will stand. The blocks will slowly slide away. Correct? So these two regions will become valley because they are becoming depressed right now. My head will become a hill. As simple as that. So this is the usual case. But this is also possible. You can have conditions like this also. So we need to understand when will this happen. For that, you need to understand why this happens. Some of you gave the answer too, isn't it? See, please understand, this is way too normal because this is supported by some stable structure. Usually, this is the case. My head is standing because my head is supported by neck exactly. So once the blocks go out, there is no problem with the head because there is proper support. At the end of the day, you have the entire crust and then your mantle and everything. This is not going to fall off. So, and the second condition, you will get that landform provided the neck is not there. If there is no neck, the head is going to fall down. Okay, if there is no support or no connection. So you need to create a condition where the bottom portion is unstable. And when can you create an unstable condition? I will show in the next slide. Both are possible, but second one will happen when you make it unstable. How do you make it unstable? When convective currents are there. So once there are convective currents, they slowly start to heat the crust. Once you heat the crust, it is going to melt and lose its stability. Fine. So this is how the convective currents are operating. You see the diagram? Tensional force. Tensional force. That's all. That's what we've established right now. So both are possible. It depends upon whether convective currents are strongly operating or convective currents are absent. So both are possible. Okay, I'll draw it here itself. So convective currents, it begins to melt and disperse out. Once you copied, use the word finished. Now I'll show you pictures and examples. So in this case, it's stable. In this case, the central is unstable. Central block is unstable. Two responses. One more, I'll proceed further. Right, good. Now, when you come across your textbooks, there are chances you might come across this word, Rift Valley or Rift Valleys. See, understand you're already studying Rift Valleys. Let me explain what is the technical definition and why Rift Valleys and fault block landscape are one and the same. Look at the definition right now. Characterized by connected networks of hosts, elevated structures, grabens, okay, depressed structures, half graben. Half graben is the depression is still incomplete. I mean, it won't get a proper symmetrical structure. It might be tilted like this. One area will be moving in, one area will still remain elevated. See, that's what is in nature. You might get structures like this also. A block which one side it is sinking, the other side it is not. Perfect symmetry is not always possible in nature. Mostly it is asymmetrical. This is called as fault block landscape. Now, this word is interchangeable with Rift Valley landscape also. Then you ask me what is the difference? Only difference is Rift Valley landscape extends for thousands and thousands of kilometers. Okay, we will see an example of African Rift Valley. It starts as far as Tanzania and Ethiopia, Tanzania and Kenya, and it moves as far as your Red Sea. So it's very extensive. So if the same fault block landscape is very larger, we call it as Rift Valley. Both Rift Valley landscape, both terms can be used interchangeably. Now for examples for fault block landscape, I'll give you 2 to 3 major ones in different parts of the world. So first we'll start with the best example itself. I'll show you Africa itself, That's the place where your Rift Valley landscape is well developed over extensive kilometers. Is it clear? First we'll see the map. And then we'll go to the mountain example. Yeah, I think this is good. Fine. Okay. Right. Now pay attention here. I think you're reading the countries. Mozambique, from map reading, of course. Tanzania, DRC, Democratic Republic of Congo, Kenya, Ethiopia, Uganda, South Sudan, and then you move to Eritrea. Here is Sudan. If you pay attention, this is my Rift Valley. Okay, there are two Rift Valleys in Africa. Africa is actually splitting open, I told you, isn't it? Africa is splitting open. Like this is, you would have written that in your divergent margin. So this is my West African Rift Valley, this one. Okay, it's splitting open. Got it? At the same time, you take your East African Rift moves long areas. Okay, how far, you ask me? Well, it travels over a very high distance. Look at the segment. It extends outside to Ethiopia. From Ethiopia, it moves even north to Eritrea. And from Eritrea, it moves as far as Red Sea. Red Sea did not exist few million years ago. It was actually closed. The area between Saudi Arabia and Egypt was closed actually. Red Sea is a result of rifting open. Okay, the Rift Valley doesn't end here. You know where it goes? It goes as far as Israel. The rift is extending outside. And then it goes as far as Israel. And Dead Sea, which you are familiar with. You might have heard about Dead Sea, of course, in Israel. Dead Sea is actually a Rift Valley lake. Okay, you've opened it up and there water storage is there. Okay, so how do you, if you want to represent using a diagram, how do you represent it? Possibly a diagram, I'll draw it now itself because you've seen the landscape. So in Africa, you have both a West African Rift and East African Rift, right? So, or Western Rift and Eastern Rift, both are part of East Africa. So on one side, you have a rift, land is subsiding. Okay. So here is the Western Rift. High temperature, crust is melting. High temperature, crust is melting. Okay, so what happens in these two regions is, if you think back to the climate is quite humid. For example, these are the peripheral regions of the equatorial region. So you'll either have savanna climate or Sudan climate, or you will have your tropical marine climate. So rainfall is quite good. So these are depressed areas. Depressed areas, if there is rainfall, okay, it's a humid region. So if you get rainfall, in the depressed regions, water will begin to collect. So that is why you have lakes in this region. Okay, West Africa, if you look, like later, please refer to your Africa physical map from Atlas. If by any chance it's there by the side, just go to Africa physical map. You'll be in a position to understand. There'll be Rift Valley lakes in the Western Rift, because water will collect in depressions. Here also, you'll find lakes, Eastern Rift. Now, in the middle, you find a depressed section, not technically a rift. It's not a Rift Valley lake, actually. It's a very large lake. This is Lake Victoria. Remember Victoria, map reading? Before dancing in Tanzania? Right there. Victoria is not a Rift Valley lake. That's a surprise. It's located in between Rift Valleys. Okay. So use the word finished if you're done. So Africa is the best example you can quote in your answers. For fault block landscape, very extensive. So in future, you'll find two African continents. Africa will split wide open. Okay, you'll find an African sea in the middle. Only thing is, we won't be there to see that day. Okay, but it will happen, provided the plate tectonics or the convective currents will be operating today. Right? So I think you're getting the connection clear. Some parts of the world should be more comfortable right now. Now let me show you two more countries. We'll go to Iceland and then to United States. After Africa, one of the intensely studied landscapes is the United States of America. But before that, I'd like to show you Iceland. Because Iceland, if you remember, that's where we had the divergent margin and hotspot. It's there in your notes already. So Iceland for Graben. Now, this is very good. This is quite extensive. Because now if you look at your notes, you should be in a position to understand what exactly it is. See, this is just to aid your understanding. See, this is what you've drawn in your notes actually. Look at this. Block 1 is elevated. This is block 1. The block 2 is depressed. It's running for several meters actually here. Number 2. And block 3 again is elevated segment. See, this is only few meters. This is not a mountain. It's technically host and graben. See, that's what I told you. Like this will extend for possibly 1 or 150 meters. Nearby, you'll find one more host and graben because everywhere your convective currents will be operating. Remember this. 1, 2, and 3. The diagram is just there in your notebook. 2 elevated host and 1 depressed graben extending for possibly 100 meters or so. The entire Icelandic region, you'll find several hosts and graben like these. We'll find one more. And then I'll show you United States. Because fold mountains you already know. Like when you generally ask, anyone asks you to draw a mountain, you will draw fold mountains. This is good. Because when a man stands there, you can clearly see that he is standing at the top. And there is, so with him you can have a reference point. So he's, possibly this is 6 feet height. Very extensive landscape structures. The green area is depressed, others elevated. And for United States, where exactly it is in the western part of USA, Great Basin Ranges. That's one more example, you can note it down. Great Basin Range in United States of America, right? To the eastern side of Sierra Nevada. Hold on, I think it's loading. Right. See, why it is intensely studied? Because it is in the United States of America, that's all. So, see, you can see that the field of geomorphology will really develop from the contribution of American geographers. So, first they study the landscape of that region. I think you see the word right there, California. Fine, so you know this is where you have your Mediterranean climate, San Francisco, Bay Area, Sacramento. So, to the eastern side, the states include Nevada and south of Idaho and Oregon. Okay, so this entire region. You want a reference point to the western side of Rocky Mountains. I think you see the word right here, Rocky Mountains. So this region is an entire fault block landscape. Alternately, you'll find. See, you want an example how things will be. I'll just tell you this. You know, Wonder Cake. Milka Wonder Cake. One advertisement will come. One boy will come. He'll come in different t-shirts. He'll change cap. Those who have not seen Wonder Cake advertisement, Wonder Cake advertisement not there. Hold on. Wonder Cake, we'll type. We'll see whether we can get a picture. Cake, you've not gone and Wonder Cake. Very good. Brilliant. People, you will find landscape like this actually. I am not joking. You will find landscape like this. Okay, you'll find block after block. Blocks will be arranged like this. Block 1, block 2, block 3, block 4. Okay, they'll have very, very low angle falls. They're called as listric falls. Arranged over like kilometers altogether. Certain areas will be mountains and certain areas will be valleys. You will get this over landmass. The only thing is I tried searching pictures in the morning. I couldn't find one. Okay. So let me try one more time. If we get it, it's fine. Great Basin Range. Mountain. But still, you don't get the entire... try satellite maybe. Okay, I don't know whether the resolution is good. We had the same thing in the morning also. Fine, let's see whether you can visualize this. No. Shall we try? Yeah, hold on a second. I think you might get the idea. See, I'm too close. I can't see it properly. The resolution is poor. But if you pay attention, you'll find that there are alternate streams of light color and dark color. You see that? Even a single line will be quite thick enough for this. Okay. Idume varla means nothing is coming. You see that? This is a light section, and surrounding that you find brown color. Here there is one more light section. Here there is one more light section. So you see alternate bands of white and dark going on. So you'll find mountain ranges, valleys, host graben. So these are major examples. You can have more also. So we have seen Iceland so far. In 3 examples, we've seen Africa, African Rift Valley. We have Iceland, Great Basin Range of United States, Great Basin Ranges. We have Rhine Graben. Remember Rhine River for map reading class? Rhine is actually a graben. You know, it is a depressed segment. On either side, France and Germany, it will be elevated. Rhine is a graben. Okay. Do you remember Rio Grande River? You should remember, I taught you in map reading. Rio Grande is the river which is between United States and Mexico. It forms an international boundary. This is one more graben. And New Zealand also has a fault block landscape. New Zealand is one more example. There you have elements. How convective currents makes, oh man, CIN 2088964AG, you better ask me that out at the last. Is it clear? Because you'll definitely need to tell me which part. When you simply say block 1 and 3. Can we link Narmada Valley with this? Akhilesh, you're right. That's what I told you. If you're in, I didn't intentionally tell you. Like Maharashtra and Madhya Pradesh, I didn't want to give it away. You'll learn that in Indian geography. I'll tell you. The Rift Valley landscape properly developed in India is over Maharashtra and Madhya Pradesh in the Narmada and Tapi region. Vindhya Mountains, later you look at India map. Vindhya Mountains, Narmada Valley, Satpura Mountains, Tapi Valley. It will be alternate. Mountain, valley, alternate landscape will come. Good. Good one, Akhilesh. Yes, in India, that's the best place. That's why I told you. Madhya Pradesh, Maharashtra is a proper landscape. So CIN 2088964. I'll take it out of the last because the question is, it's very difficult to interpret the question. It says block 1 and 3. I don't know which one you're talking about. Okay. Moving on. Now we'll go to the next segment, earthquakes. See, the first part will be relatively easy. Okay. So are oscillations of the Earth's crust and are caused by natural and anthropogenic factors. Natural and anthropogenic factors. Anthropogenic factors. Full stop. The natural causes are closely related to plate movements. Full stop. Okay. Plate movements. The first segment will be easy. It's straightforward. The anthropogenic factor will need to spend some time. Like next slide, I will immediately write the first segment. You won't be surprised at all. Why earthquakes happen? Way too simple. Use the word finished if you're ready. First part, straightforward. Second part requires explanation. See, now the world should make more sense. You're almost closing this. So, same convergent margin, divergent margin. Same process. Convergent margin. Powerful earthquakes. Okay. Divergent margin. Mild earthquakes. I'll write the keywords, follow up. You can copy it in case any doubts is there. You can ask me. I think it should be fairly comfortable because same diagram. Like, denser plate is subducting inside. The lighter plate is folding in. So once the denser plate moves inside, this will be heated by the asthenosphere. Because once I'm moving into this area, once I start heating, there is accumulation of a large amount of heat. The plate will begin to break down. Once you break down the plate, there is energy release. Meaning makes sense, right? The area. So ocean plates, or this can be ocean collision, ocean continent collision also. So plate sinks inside. Okay. So heat in asthenosphere. Heat in asthenosphere. Right? So the denser plate subducts. And is heated by the asthenosphere asthenosphere, causing breakage and release of energy. Breakage and release of energy. Release of energy. So the breakage can happen anywhere. You can have a breakage here. Okay, this X point which I'm drawing right now, that place you can have the breakage here, have the breakage in the middle, no problem, like anywhere. Wherever you have the breakage, there, that will be the point of energy release. That will be your focus. This is way too simple again. I'll write the description again. See, that's what I told you, isn't it? Once you learn volcanoes, once you are able to relate to mountains also, earthquakes are not really surprising because movement will create tremors. Same thing here, because I'm going to heat from the bottom, then I'm going to move the blocks, right? Move the blocks. Okay, along with that, at times I might get volcanic eruptions also. So divergent margins, the crust is melted by the asthenosphere heat. Asthenosphere heat, and the blocks are forced away, causing mild tremors, causing mild earthquakes. Mild earthquakes, full stop. I think, yeah, visibility is there. So no surprises here, even though we have one more domain. The point is this. See, this is why you go to a country like Nepal or Bhutan, or you're Sikkim or Arunachal Pradesh, your risk factor is very high because convergence, collision. A collision will take up large amount of energy. Any point of time, the Indian plate, which is sinking inside Eurasian plate, experiences more heat. There will be sudden breakage. And of course, Nepal will face problem. Himachal Pradesh and Uttarakhand will face severe issues, including Jammu and Kashmir. Okay. This is not going to be problematic. Your divergent margin, because you're not fracturing anything. Okay, not very severe fractures, not too much of heat. Just automatically, you're allowing the plate. Once your land splits apart, there will be mild tremors. This happens very frequently also. So this is not such a big deal. That's dangerous for every country. This is not much. Use the word finish if you're ready. We'll just need to address a subtle point in convergent margin. And then we'll address the most powerful earthquakes in the world. Right, multiple responses. Thank you. So this is regarding the first one. Okay, within this there is a slight difference alone, because I did tell you that when you have this subduction part, your energy can get released anywhere. You're just focusing on this section. The ocean plate can keep subducting, and wherever the heat is very stronger, it is going to melt and then breakage. So you can have an earthquake which is of shallow focus. Shallow focus meaning, like with reference to your mean sea, your surface level, the depth is quite less, or you can have a very deep focus also. Deep focus, where the point of energy release is quite away from the surface. Meaning makes sense. And this, always remember this variation of shallow focus and deep focus is possible only in a convergent plate margin. Divergent plate margin, there is no point of deep focus at all, because already the energy is going to be at the very close to the surface level, because that's where you're heating and breaking it apart. See, between these two earthquakes, shallow focus earthquakes are more powerful. I'll write that statement, no problem. Listen first. Why they are powerful? See, usually there is a misconception, because you take deep focus earthquakes, there is immense amount of pressure. The amount of pressure which you put up this area is very, very high. So here also there will be very good amount of energy release. But problem is, deep focus earthquakes is kind of several kilometers deep inside. So by the time the energy is released and it comes to the surface, a good amount of energy will be lost in this direction. Okay, because so many kilometers. But here, shallow focus earthquakes, from the point of energy release, the distance is less. See, it's like from the impact position, how far you are. You're very close, you'll face maximum impact. So even if it might be powerful, the distance traveled is very, very higher. That is why your energy, like the impact is going to be less, because I'm going to travel quite some distance. Okay, so shallow focus earthquakes are more powerful, and have severe impact. and have severe impact because they are close to the surface. They are close to the surface compared to a deeper focus. Compared to a deeper focus. So energy release is very high. Okay. More impact. But the most powerful earthquakes in the world are not in convergent plate margins. They are actually in one more plate margin called as transform plate boundaries. That's what we'll see next. I use the word finished if you're ready. Right, thank you. The last part before we go to anthropogenic factors. Transform margins produce the most powerful tremors. The most powerful tremors. Full stop. This is because they act over a zone. Act over a zone. Full stop. When the rocks are stretched beyond their elastic limit, elastic limit, they try to regain their original position, producing strong tremors. I'll draw the diagram here. Then I'll add the last two lines will require explanation, right? Okay, block 1 and block 2. So this time, this is their movement. Here we are. I will read this statement one more time. I think that will give you enough time for copying. Then I will explain, okay? Transform margins produce the most powerful earthquakes. This is because they act over a zone, full stop. When the rocks are stretched beyond their elastic limit, they try to regain their original position, producing strong tremors. Is it fine? Now do pay attention. Then maybe if still not copied, you can do it later. See? This is what we call a strike slip movement. This is not striking slip, this ruptures. So these earthquakes are very powerful. First reason, as I told you, you're not talking about a single focal point. You're talking about an entire zone. So if you have an entire zone of rocks, all the rocks are going to get stretched in this region. So your energy release is going to be tremendous. And second thing, it is not a subsurface, not a very strong, deep subsurface phenomenon also. All the rocks which are going to get ruptured are going to be in this very close to surface. That is why energy release will be extremely higher. That's point one. And second one, like to explain the second point only, I've drawn this vertical diagram. See, thing is, we are talking about a rock which is embedded like under the surface. Okay, under the surface. And you have one force which is moving in, like the strike slip movement. You see that? Like I've drawn it in the reverse way, but the point is the strike slip movement. You see that? So one is moving up and one is moving down. So what will be the impact of the rock here? So first, the rock is perfectly horizontal. Okay, consistently there is movement. Is it clear? See, every material will have an elastic limit. You take my hand for you take the palm for example. There is a certain level of limit I can bend without any pain. Now, if I provide more force, I start to feel more and more pain, and slowly, if it's very severe, then eventually the fingers are going to get cracked and then fractured. So you'll be in a position to completely break over. Same thing happens with the rock also. It will try to retain its original position. Like it'll try to maintain the same size up to a certain elastic limit. But you break open completely, then for a second, just for a few seconds, it'll try to come back to its original position, isn't it? That is when you release the energy. So finally, the rock gets completely deformed. You've broken it totally, just like you fracture the hand. Meaning makes sense. So as long as it is within the elastic limit, it's totally fine. Let's say up to this, you can stretch it. No problem. You stretch it beyond it, then it gets broken down. So in that few seconds, where it comes back to its original position, that's when the energy is released. Got it? That's what you've written in the last line. The rocks try to regain their original position, which is not possible. You can't regain the original position, but when they try to move along in the direction, you get the energy release. Is it clear? So use the word finish if you're ready. We will go to anthropogenic factors. Right. Thanks for responses. Now, usually we have this connotation that human beings are way too small to cause earthquakes, but actually we do. See, there are two factors which are quite consistent where we can cause tremors. And note this, even the earthquakes which are caused by anthropogenic factors can never be powerful. It cannot be as powerful as this or as powerful as this also. No. Okay. The earthquakes will be affecting a smaller area, maybe 3 villages, maybe one single town, isolated events, but we can have the potential. So there are two reasons, anthropogenic factors. Anthropogenic factors can cause earthquakes. Number one is dam construction. Dam construction. This is quite dangerous once if it is done in the wrong area. There are two ways it can happen. It can trigger events. Okay. After drawing the diagram, I'll tell you what it is. Land. The blue color thing is dam. That's all. This is water. Okay, fine. Water is stored. People, let me explain. Then you copy. Wait. See, this is not technical. This is way too subtle. Okay. When you go for dam construction, you do it for several purposes, but the primary reason is water storage. And you will do it in an area where you have a necessity of water conservation. That is where you go for dam construction, isn't it? You take a place like Uttar Pradesh or Bihar, you'll not find dams. You wouldn't find it. Later you try to check it. Or even if you find it, the number will be very, very less. Not because it's a plain region, technically, you'll not find any hydroelectric potential. Also, necessity is very less. There is very good amount of rainfall, large amount of water. So the first problem with dam construction is you will construct a dam in an area where both the soil and the geology of the region, the rock structure, really haven't seen large volume of water for quite some time, which means the rocks are not very comfortable in handling a large volume of water. That is the first thing. Number two, water adds enormous amount of volume. Okay, the weight is quite tremendous because if you look at the size of artificial lakes or artificial reservoirs in the map, it will be even big than your natural lakes also. Natural lakes is not a problem. As the word says, natural. Wherever your natural depressions are there, their water is going to collect. This is something which you create artificially. So the amount of water volume addition is going to increase enormous amount of weight. You can create earthquakes just because of the weight of the water volume. Basically, that's reason number one, strongly. Reason number two, usually when you go for geoengineering studies, it is not enough that you check only the top surface layer. Several kilometers beneath, the bottom surface might be under enormous amount of stress. Like you might have folding at the bottom surface. That's what I've drawn like this. You get the idea? And once you get a stressful condition, water can actually release the stress. How? Water is a lubricant. Think what happens whenever you have your ring which is stuck in your finger. Maybe it is way too short, maybe your fingers were big or the ring was very small. What you do is you use soap. You will tell me, sir, soap is the lubricant here. I know, but in a dry land condition, water acts as a lubricant. So once you start storing water, water begins to percolate down to several layers. Slowly. It doesn't happen in single day. Okay, let's say the project is done for 20, 50 years. It stays there for 50 years, slowly. So the stress which is accumulated, once water begins to lubricate this area, all of a sudden the stress might get released. Maybe it becomes flat again. Normal, the accumulated fold becomes flat. So all of a sudden energy is released, and this energy release is nothing but your earthquake. This will cause oscillations on the top surface. Please understand, India has a bad experience itself. Koyna Reservoir, I'll write the name, Koyna. Koyna Reservoir in Maharashtra was considered as a reason for an earthquake, because in and around the region, after dam construction, it was believed that it was a leading factor. See, because Maharashtra, Madhya Pradesh is a faulted zone. After a Himalayan region, the risk factor is quite high there. So that was not a very acceptable project. Meaning makes sense. So two reasons: large water volume, disturbing stability because it has a large amount of weight. And second is, if the subsurface layer has immense amount of stress, water can percolate downward and release stress. I'll write both of them. This is reason one. Water volume adds more weight, disturbing stability. Number two, water percolation to deeper subsurface layers can release stress, causing earthquakes. Stop. Two ways it can happen. The dam construction is not a joke, people. Like, there are several environmental consequences and basic geological consequences too. Use the word finish if you're done. See, it's not that India is the only country which is having problems. See, any country starts with a project, it will face issues. If you take United States, it's not that United States of America is always clean. USA has had its own fair share of problems when they started dam construction. I mean, I'm talking about several 50, 60 or 70 years earlier. They were way ahead. There was a dam construction project in thanks for the response. See, there was a dam construction project in 1950, 1960. It was a disaster in USA. I'll tell you what they did. Just know that every country makes mistake. They went for dam construction. Okay. You know what was the bottom base rock? Big geological mistake. Limestone. Calcium carbonate. Calcium carbonate dissolves in water. You know what happened? Water started dissolving calcium carbonate, got to seep in. After it got seepage in, overcame the dam and water came in this side. The arrow mark I've drawn like this. Basic geological error. It caused severe destruction. Every country thing is, you learn from the mistakes. You don't repeat it again. Okay, not the developed countries are also clean. Everyone makes errors. Second one, unregulated deep mining. This will be fairly simple to understand. KGF. When will chapter 2 release, man? Bullet learn is going and smoking. Release faster. I still remember the meme. If I want to, smoke one cigarette, I'll need to shoot 8 Jeep. All the Jeep will burst. Only then I can shoot. So I can smoke. People understand, then you can copy. See, mining is not a problem. Deep mining is also not a problem. Look at the word I've written there, unregulated deep mining. First, let me write the entire slide, then you can copy it down, because this is not a conceptual part, just a basic idea. The first type of mining is open pit mining. You will do open pit mining under two conditions. The resource which you're looking for is only few meters below the surface. Second one, the resource extends for a very large area. Very, very large area, extensively. You know for sure that there is large amount of coal. For example, this is the open pit mining is what is done in places like Chhattisgarh, Jharkhand. There is large amount of coal. You go to Neyveli in Tamil Nadu, lignite mining is done like that. Bikaner in Rajasthan, lignite mining is done like that. So what you do is you just till the soil, quarrying. You have your quarries, you just dig in and just open. That's all. Go few meters deep, you'll get enormous amount of resources. Meaning makes sense. You're able to do that only because you're assured that you will get resource. Because once you start tilting the soil, you cannot do agriculture for the next 1,000 years, 1,000 or millions of years, because the soil quality is that's all, it's done. Open pit mining. When smaller depth, you find high concentration of resources. Open pit mining is more polluting. That is the problem. Damaging to the atmosphere, damaging to the ecosystem, all that. Soil is dead, that's it. So more damaging to the ecosystem, but not earthquake problem. Deep mining is more problematic. Deep mining is this, completely reverse. It's found several kilometers beneath the surface. And second thing, it is a localized, small area. Very, very small section, maybe this is the resource. That's why I told KGF, no? What they'll do is they'll construct one opening on top. Okay, they'll go very deep. Lift will be there. The Captain America, and after lift, they'll construct tunnel. From the tunnel, workers will be having these, headgears and all that. The light will be their torchlight. Then they start excavating. This is deep mining. Now pay attention. See, if you look at oil and natural gas companies in the world, understand the economics behind. 5 years or 30 years earlier, they were making really good profits. Today also they make really good profits, but there is a subtle difference. Before 1990, even if environmental awareness was not a rage, you did not even have many environmental organizations. Later, when you study IO, please be cautious. Look for most of the environmental organizations and treaties. It will start from 1990s. Governments become more aware. That is when more demand is paid on sustainable development and more demand on private companies to be more cautious. So currently, if you look at profit margins of several oil and natural gas companies, it is between 15 to 20%. They don't make too much of profit. So if you want to make profit, it's not possible that you follow the rules all the time. You'll try to mend the rules now and then. Let's say that you've invested money. Infrastructure is already stable. See, this requires too much of money. You need to set the processing plant on top. Okay, you need to exploit it, and then you need to process it and then export it outside. Let's say you've invested 3 years, 3.5 years, crores of rupees. Later you find that the resource is not enough. Then what do? Already infrastructure is stabilized. If you find some more resources, you can increase the profit margin. You'll start to blast here, blast here, blast here. See, unregulated. Without proper research, if you start to expand in the interior area, then you are completely destabilizing the structure. So much of dynamite explosions, the entire surface will collapse on itself. People will get killed, of course, but at the same time, you can create earthquakes. Meaning makes sense. So unregulated deep mining will result in collapse, as subsurface stability is compromised. Subsurface stability is compromised. See, always know the reason. Always know the reason why people are doing something. Why is unregulated mining a rage? Because they want to expand their profit margins. Can we say July 16, 2021? July 16, oh, KGF 2 release. I couldn't make the connection. July 16, 2021. Fine. People, can we say Machu Dam failure? Okay, I really do not know Machu Dam failure. Pardon me for that. Now, I don't know the event which you're describing. On July till I need to wait. January only, no man. Fine, it'll run. Already January over for 2021. Use the word finish if you're ready. This is more environmentally problematic. Keep that in mind. Okay. Right, I think you've taken down. You have 5 minutes, so I'll just introduce one topic. Then break after that isostasy will be done. Right. Good. 3 definitions. Okay. Weathering. Then you take your break. Is the disintegration and breakdown of rocks. Breakdown of rocks. Erosion is the transport of sediments by an agent. Wind, water, glacier, anything. Glacier, etc. Next, mass movement. Mass movement is the movement under the influence of gravity. Movement under the influence of gravity. Influence of gravity. Full stop. Erosion, weathering, mass wasting. I'll read the definitions again, then I will give you clarity. Weathering is the disintegration and breakdown of rocks. Erosion is the transport of sediments by an agent, wind, water, glacier. Mass movement is the movement under the influence of gravity. See, all these 3 are degradation processes. When you say weathering is disintegration, we are talking about something which happens at the same place. So if you have a mountain range, due to variations in temperature between day and night, due to the operation of some chemical reactions, a rock of the mountain can just break down in the same place, can just stay right there. That is called as weathering. When we talk about erosion, the factor of transport is involved with an agent. So from the mountain, if a river is transporting the sediments from point A to point B after 50 or 60 kilometers, you call that as erosion, eroding. So erosion, always remember, one person is involved. That is erosion. Mass movement is simply attraction by gravity. See, any slope, the slope can be gentle, the slope can be steep. If this is going to be a land area, everywhere you take, maybe a steep slope, steeply sloped mountain is there, or you have a very gentle slope hill, anywhere, because of the presence of slope, you will naturally tend to get attracted towards the bottom. That is called as mass movement or mass wasting. Example of mass wasting is landslide. Okay, landslides, yes, they will be accelerated by rainfall. But at the end of the day, landslides are technically a creation because of the slope component which is present right here. You just need to understand one single point, have that very deeply in your head as conceptual point. I'm going to ask you a question in prelims, it will be like this only. 1, 2, 3. All the 3 processes are independent of each other. Keep that word independent in your mind. You need not even write in your notebook. It is not necessary that weathering should happen, only then erosion will start. Not necessary at all. See, if the water is very powerful, you need not even disintegrate the rock. Just by the velocity of the water, it will just take everything out. Not necessarily that weathering should happen for erosion. Meaning makes sense. At the same time, it is not necessary that weathering should happen, only then mass movement should proceed. You take soil, for example. Soil will naturally slide down. Very slow movement, simply because of gravitational influence. So 1, 2, and 3, all the 3 processes are dependent. Dependent meaning one will aid the other. If there is more weathering, yes, of course, there will be more erosion, there will be more mass movement, no problem. One will aid the other, but it does not mean one should happen or one is dependent on the other. Okay, it's not necessary that erosion will happen only if there is weathering. If they give this word only, or this will commence, or like mass movement will commence only after weathering. No, it's completely wrong. Or mass movement will happen only after erosion, not at all. 1, 2, and 3, all these 3 will support each other, will aid each other, but each is independent on its own. Got it? So before the break, let me tell you what else you should need to do for geomorphology. Ready? Fundamentals of Physical Geography, 11th NCERT, Volume 1. Coaching Lyon. Chapters 15 to 25 is for climatology. Okay. Chapter 1 is introduction. Chapter 2 will again start with the basics of origin of the universe. Pay attention. 3, 4, 5, 6, 7, 8 to 11, I think. 13, 14. 12 is world climate. People, this is climatic regions. This you should have read already, I believe so. 8 to 11 will again be climatology concepts. So for climatology, class notes, chapters 8 to 11, chapter 15, 25 in climatic regions. Don't ask me which NCRT. எழுதி போட்டிருக்கீங்க 11th volume 1. கடைசியில் முடிச்சு after completing people will ask, sir, which book? Number 2. Origin of the universe you'll eventually need to read. You won't get possibly questions from that, but it's more of a revision introductory part. Plate tectonic theory, earthquakes, volcanoes, all that will be in chapter 3, 4, 5. After class notes, read this also. Thing is, diagrams may not be as elaborate as we saw here, but I told you, both are complementary. You have enough amount of diagrams for this. 6 and 7 are there, no? This is geomorphology. These chapters 6 and 7 and 3, 4 and 5 is there, isn't it? That is what is there in chapter 1 to 2 of Coaching Lyon. That is why I told you, 1 to 12. Don't learn this Abhin solely. I'll tell you the reason why. And I should tell you to what extent you should learn also. See, chapter 6 will be endogenetic, exogenetic forces. Chapter 7 will be landforms which are created by different erosional agents. For example, if river acts over an area, what are the landforms which are created? There will be river valleys, there will be delta, there will be meanders and all that. What are the landforms created by glaciers? That will be discussed in chapter 7. 6 will say what are the forces which are acting on the earth. People listen. From chapter 6 and 7, last question in UPSC came in the year 2013. One question they asked. Is it clear? That was in prelims. Mains from 2013 till this year. 2020's mains was written right now. Till 2020, last 8 years, no question in mains. Last 7 years, no question in prelims. One question was last in 2013. Got the idea? I think this is 8th year right now. That is why we are not investing time. But always remember, you should not leave the ball and go. Then this year UPSC will ask the question. So what should you do? Read chapter 6. There is a difference between reading and learning in detail. Read through once chapter 6. Read through once chapter 7. And I want you to create a table. What is a table? See, if I'm going to ask you a question after this long, I will touch only the fundamentals. Okay. Make a chart like this. Wind or running water. Let's start from this. Running water. It is nothing but river, wind, groundwater, glacier, waves, erosional landform, deposition landform. This you need to fill after learning chapter 7 or reading chapter 7. Read that. See, thing is, if I give you one landform, you should be in a position to say whether it is an erosion landform or a deposition landform created by whom. For example, Cirque is an armchair shaped structure, an erosional landform due to glacial erosion. I mean, due to the weight of the glacier. Okay, you take something called as a spit, lagoon. These are deposition landforms created by rivers. You take valley, erosion landform which is created by rivers. Delta, deposition landform which is created by rivers. You got the idea? You read through chapter 7, you'll automatically get it. Because everything they start like this only. Running water, erosion landform, they are described. Valley, river, terrace, meanders and all that. Deposition landforms will be there. So you will get, for example, 4 for this, 4 for this, 4 for this, 4 for this. So 4, 4 in either side. Sometimes it will only be 3, 3. Keep this chart with you. Once you've read the chapter twice or thrice, multiple times, just read through, not learn and read. Just read through. You'll get the idea, able to relate to it. Then after that, just revise this chart now and then. That will be more than enough. Because 8 years they haven't asked question. If I need to explain this, I need to explain 1 or 1.5 classes. Even last year we stopped teaching this part. Because if you're going to invest time, it has to be productive from exam perspective. We're not trying to be experts in geography anyway. Keep the chart with you. This is more than enough. Okay, never ever leave this and go. That will be wrong. You never leave the ball. Prepare. Okay, prepare, but this basic level will be fine. Can I use Savindra Singh for geomorphology? Not required. That's an optional thing. So optional geography students can study that book. Not required here. Okay. General studies, this is more than enough. Take a break for 5 minutes. We have a small topic, isostasy. After that, I will enter oceans. 5 minutes. So last unit, oceanography, after 5 minutes. There are so many terms in geomorphology in NCRT. Amma, yes, that is what I've told. Landforms. Each and everything will have 8 to 7 landforms. Yes, of course. Padikinu, you should learn. You have any doubt in terms, you ask me, I'll explain. For marine climate, which book we need to follow? For marine climate, you're talking about tropical marine climate. Tropical marine climate, when you learn tropical marine climate, please make sure not to learn monsoon. Tropical marine climate will only be half paragraph in the chapter number 16, I think, 16 or 17 in Gocheng Leo. When you learn that, read that half or one page alone. Indian monsoon, you learn it in NCRT and follow Karthikeyan sir's classes. Okay, because Indian monsoon is not given well in Gocheng Leo. Slide 12. Okay, I'll just go there and then give you 5 minutes break. One important question. That means should I study only chapter 2 to 11? Should I leave the others? Adha, varai. People, listen. For studying world climatic regions, which one? People, listen. I thought I will say this at the last. Adukulla. See, chapter number 12, you'll find something called as world climate. In that, they would have given Köppen's classification system. Köppen's climatic classification system, UPSC has not asked in the last 8 to 9 years. General studies, it has pretty much vanished from the topic of discussion. Got it? This is for optional. Chapter 12, world climatic region, world climate chapter. I think it is world climate. If the chapter number is different, don't come and ask me later. You told 12, it is different in the book. Understand clearly well. World climate, there will be a chapter. You can ignore that. Climate change, you can ignore that. Why? You will be studying that in detail and environment. Not a problem. Climatic regions, chapter number 15 to 25 in Go Cheng Liang's Certificate, Physical and Human Geography. Point done. Don't ask me the question again on climatic regions. Last one, chapter 13, 14, oceans. Should learn. Don't leave. Okay. எடுக்கவே இல்லை அதுக்குள்ள should I learn only 2 to 11 we'll leave. People. For now, moving on. Okay. I won't explain this ever again. Now there is one more question. Should we study all the chapters of NCERT 11th standard? I have clearly told you which chapter to learn and which chapter not to learn. Okay. I'm not going to answer the question. Okay. Moving further. Now there is last topic for geomorphology called isostasy. I'll write the concept, then explain. It is the equilibrium. It is the equilibrium between upstanding and low-lying structures of the earth crust. Structures of the earth crust. Full stop. One more time, just one statement, so it shouldn't take too much time for copying. It is the equilibrium between upstanding and low-lying structures of the earth crust. That is called as isostatic balance. We'll understand the origin of the problem, then straightforward we'll jump into the concept. It's a very simple concept. Pretty hard to conceive, but see, you take a building which is a 4-floor or a 5-floor building, or even the 100-floor building in New York, you need to provide very firm foundation. If the foundation is poor, the building is going to collapse, right? So whenever I ask this question to students for a 5-floor building, what is the level of foundation? They will say that it depends upon soil quality. Some will say 2 feet, some will say 3 feet, some will say 1.5 times the, or some ratio they will give me. I'll never understand. But point is, you need some sort of foundation for the building to stand firm, right? So without that, it is going to collapse for sure. A firm foundation is required. It will vary, of course, depending on soil quality and all that. That time alone, the civil engineer inside that person will come out. Enough. Sit down. Okay. See, the point which I'm trying to convey is, if for a 5-floor building, you need a firm foundation, what about this one? This is Mount Everest. What about the foundation for this? You might be laughing at me right now. This is a stupid question. Mountains are natural landscapes. They can stand. People, but if you think about it, it's not a stupid question. I can ask you this, because if for a building you don't have a firm foundation, the building is actually collapsing. A mountain which is composed of high level of complexity of rocks, which is facing high level of tensional forces and compressional forces, if you think properly, it shouldn't be standing at 8,848 properly. Forget this single mountain. You know the extent of Himalayan chain, isn't it? Himalayan mountains is a very complex folded mountains, and you have several mountains together. You'll find complex structures, one over the other. And not all of them are straight. Some will be inclined like this. One person is straight, one person is completely inclined. You'll find mountains like this. So how on earth they are standing? Now, if you think about it, it's a reasonable question. If a building can collapse, how do large mountain chains maintain their stability? This was an important question mark, not right now. In the later part of the 19th century itself, and research started with India. When the Britishers arrived, they started researching with reference to Himalayan mountains. And based on that, several theories were proposed. That is what is the isostatic equilibrium study. Now look at the definition. It is the equilibrium between upstanding and low-lying structures of the earth crust. So how on earth are larger structures able to maintain their stability? So the final theory was proposed. Before I go to the theory, I will give an analogy. If you understand the analogy, understanding the theory is very simple. We'll take a water bed. Water bed. Maybe you're in a theme park. They have this. I'll take bricks of the same size and same weight, place on either side. Maybe 2 here, 2 here. When you place weight on this waterbed, it's a fluid medium, of course. There will be some amount of depression, correct? Some depression is there. Here also there is some depression. My question is very simple. I mean, not a question technically. I'll explain the process. If you've understood, use the word understood. I'll do this. I'll take one brick from this side. Okay, I'll take this brick out. I'll place that weight here. Now, when I place this weight over this one, there is a natural tendency that due to addition of weight, there will be more depression, correct? Due to there is more depression, what is getting compressed, which means water will migrate. Once water migrates, this will slightly get elevated. Slightly, the depression will reduce, slightly move up. Any doubt in this process? The theme park waterbed, the brick. Fine, thanks for the response. This is clear, no? See, actually, this is what is happening in the earth. Don't believe me, I will show. The waterbed is your asthenosphere. Over the asthenosphere, you have the crust. And crust is not having the same weight everywhere. Certain areas the weight is higher, certain areas the weight is lower. Mountain, plateau, and then plain. Got it? So in a mountain, whenever the structure is elevated, you will find definitely more erosion. See, let me explain the whole concept. Then if doubt is there, we'll clarify at the end, possibly 720 or 725. Until I finish, please don't interrupt me. Erosion. Once there is erosion, naturally in the plain region, there will be more deposition. Deposition. So here, there is reduction of weight. Whatever weight is there, I'm taking it away. Okay. Reduction of weight. As you saw in the previous case, I'm taking that rock out. Here, there is addition of weight. Right, here, addition of weight. Addition of weight. Due to addition of weight, as we place the third block, there is more compression here. Got it? So there's more compression. Once there is more compression, automatically there will be migration. Migration of whom? In the previous case, we saw water. Here we are talking about molten material in the asthenosphere, at times magma. Okay, technically it is ductile solid medium, but you are adding more weight, which means rocks will actually migrate. Migration of magma very close to the upper mantle. Magma begins to migrate, and what will happen? Pay attention, last point. Once magma migrates, the mountain will slowly get elevated. Let me finish. Wait. You know what question will come? So you're saying that if erosion happens, mountain will move up, which means Himalayan mountains will move. Wait. See, that is not the point I'm trying to convey. People understand any elevated structure, if there is going to be erosion, height of the mountain will decrease. It will become a small hill after millions of years. I'm not stating that point. The point I'm trying to state is, if there is erosion, there will be a counterbalancing force, and that will try to stabilize the mountain up. You get the idea? Point number 2, you'll have a wrong impression that this is more heavy. Correct? Because you will see that mountain is there, which means this should be more heavy. This should flow in the reverse direction. Please understand, Bigger size does not mean it is actually heavy. Your continental crust is much lighter. Okay, the density of the mountain will be very, very less compared to the density of the plain region. Why? Because in the plain region, there is more compaction of sediments. Large number of sediments come together, so over layer by layer, they get compacted. This is much denser. Because of that, this is heavy. You take the mountainous region, for example, mountain, the crust is actually expanded, which means the density will be less. Okay, this is heavier. Don't misjudge it based on size, and please don't put that question in the chat box. And second one, I'm not saying that the mountain's height will increase. No, it will experience some amount of elevation to balance itself. Okay, erosion will finally degrade the mountain. Got it? Now take this. If you're done, use the word finished. I want to address one more point in the next slide. I don't want those questions. I've addressed both of them. Usually I get that only. Density of plain is higher than density of mountain. Keep that in mind. Density of the plain is greater than the mountain. I'll write it. Density of plain is more than density of mountain. Because plains are more compaction. Okay. You might be thinking, this seems to be an outdated concept. Why are we discussing this? See, because we might be facing trouble, and there is one country in the world which is already facing some trouble. We'll see what the country is also. Right. Thanks for response. Moving on, and I will tell you the relevance for this topic. This might seem totally irrelevant with reference to all the topics we run. It's a main topic. We've been expecting questions for some time, but it never came. This is relevant not because large-scale landscape changes are taking place, but only because of anthropogenic-induced climate change. Let's take Antarctica. This continent has enormous amount of ice caps. See, and try to visualize the range of it. The thickness of the ice cap over Antarctica is average. It varies between 2 to 3 kilometers. Average. See, at times when you see the numbers, you won't realize how big it is. When I say average height is 2 kilometers, it is more than Western Ghats. You're realizing how much thickness it should be. And Antarctica is the 5th largest continent in the world. So the amount of ice weight which you have over Antarctica is very immense. Now picture this condition. Let's say there is increase in temperature for the next 75 to 100 years. Consistent heating because of anthropogenic emissions. What will happen? You will have ice sheet melting. So slowly ice will melt away. Once ice melts away, what will happen? You're reducing weight. Once you reduce weight, Antarctica will rise up. Again, listen to the words I use. I use the word Antarctica rises up. Again, people counteract with this question. Because of glacial melting, there will be sea level rise. If sea level rise, land will submerge. How will land move up? People. Due to glacial melting, there will be sea level rise. But due to sea level rise, Chennai will go underwater. Mumbai will go underwater. Kolkata will go underwater because the elevation is less. Antarctica will rise because the weight is taken out from Antarctica. You take this out, naturally this will increase elevation. Meaning makes sense. Now automatically you get a counteract question. Fine, if Antarctica rises, what is the problem? Antarctica rising up is not a problem. Problem is in the Arctic Circle. Let me just show you. Because we don't live in Antarctica. We only have research stations. But Arctic Circle is a serious issue. Look at this. See, even though you might have learned these countries, you're looking at from the North Pole perspective, so it makes more sense. Greenland, Baffin Islands, this is your Hudson Bay, so Labrador, Victoria Islands, so this is your Queen Elizabeth Islands, Canada. Come to the other side, you find large parts of Russia, so you'll find Murmansk also. Murmansk is right here, Murmansk is ice-free. Map reading we saw. Okay, and these regions of Russia. The thing is, you will find severe infrastructural issues if all the ice in the Arctic region is going to melt, because people live here, people live in Canada, people live in countries like Sweden, people live in countries like Finland. Let's say you have a house construction, a bridge is there, you have your electric poles, maybe underground cable. What will happen if land rises for even 1 meter? Your entire infrastructure will get destabilized. This is an issue for Finland right now. Not serious, but Finland will face consequences in the future if the ice caps which are present in the northernmost part of Finland begins to melt away. So it might not look serious right now, but 75 to 100 years, if all this weight over Arctic region is going to get dislodged, parts of Canada, Greenland and Finland, including Russia, might actually experience elevation. Think about this. Even a 2 meter, 3 meter rise, your building is there. Suddenly, if your house goes 1 meter up, what will happen, man? All your infrastructure will get damaged. What about your water connection, your tap connection, electricity, wires, everything? You will get accidents. So that is something which we're generally worried about. Now, if you look at the topic, it doesn't seem childish anymore, right? It is serious for the Arctic Circle, people in the Arctic Circle. Okay, so that ends the topic of geomorphology. Now we will step into oceans, the last part. So today, at least the marine provinces we can finish, then basics of salinity for sure. Oceanography. So next Saturday and Sunday, Saturday one session, Sunday one session I can wrap this up. Then you can step into India. If you've understood world geography, India is way too simple. India only application. Okay, so first we'll study marine provinces. Marine provinces are the broad landscape divisions underwater. They are continental shelf, continental slope, continental rise, and abyssal plain. So first we start with geomorphology again, like geomorphology of the oceans. Not in detail, but more or less the overview. So if you dive inside water, what are the broad classification? See, just like we have mountains, plateaus and plains over land masses, this is how we differentiate them underwater: continental shelf, slope, rise and abyssal plain. Use the word finished if you're ready. Okay. So if you're planning to rent any land in Greenland, don't do. Or planning to settle in Greenland, not advisable at all. Okay. You might be thinking, I'm going to get civil services, why do I go to Greenland? Maybe you'll get posted as a foreign service officer in Greenland, man. So what exactly is continental shelf, slope, rise and abyssal plain? This is continental shelf, continental slope, continental rise and abyssal plain. 4. Take this down. Draw a small diagram. I've drawn it extensively. We'll go one by one. The line is to indicate that it's underwater. Okay. Shelf, slope, rise, plain. 1, 2, 3, 4. Shelf, slope, rise, plain. Here we go right now. First is continental shelf region. Continental shelf. Is an extension of the continent into the oceans. The average width of the shelf shelf is 70 kilometers. The slope is very gentle. It's very gentle. Global average is 4 degrees. I will explain. Hold on. Continental shelf. Use the word finish if you're ready. Two responses, right? I think you're ready. Okay, fine. So continental shelf is technically an extension. Extension meaning, let's say picture yourself standing on the beach. Okay. Now, when you advance towards the beach, of course, the water level will suddenly increase. But you will note that if you continue moving, the land is not going to fall in this way. That is, if you're standing here, it's not going to fall like that. Is it not? Like if you're a very tall man, let's say you're 200 feet tall, and from the beach section, if you continue walking inside water level will only slowly increase, possibly from your feet, then your knee, thighs, and then it comes close to your neck. That is what we call as continental shelf. That is simply an extension of continent into the oceans. Meaning makes sense. So the second point you'll need to say is it's very gentle. That's the point I'm trying to do. You never have this. It's not that if you keep walking, you will fall down immediately from the sea. You know, people, the flat earthers had this idea. If you keep moving inside the oceans, immediately you'll fall down. It doesn't happen. Able to visualize this general idea. That is shelf. We'll just see the Atlantic Ocean to drive this home and understand the difference between two regions. Why in certain sections continental shelf is broader, why in certain areas continental shelf is narrower. Okay. So this you will study for India also, between western side and eastern side, narrow versus broad. But let me introduce for the global level. Atlantic Ocean is a very good case study. So the Atlantic versus Pacific. South America is a very good case study. Hold on. Right. We'll take South America. I think you've seen this. See, forget the very dark blue color things. That indicates the oceans. If you're standing in Rio de Janeiro and you advance towards the Atlantic Ocean, your height doesn't change immediately, right? Slowly you will see that there is a light white color, then the white color, then it slowly becomes darker, which means very slowly there is significant change over hundreds of kilometers. This is my continental shelf portion. That is away from land, close. This could be possibly 150 kilometers, very, very wide. On the other hand, if you take, you don't find that luxury at all. See carefully. Like you do find something, but it's more like a small dot. Right? So your shelf portion is not the same between eastern coast and western coast. Can anyone tell me why? I am saying this, I'm asking you this question because I've taught climatology and geomorphology. So you can try to answer. It's very narrow on the western side, quite wide on the eastern side. Any reason why? Few seconds I'll give you. If anyone can try. Good answer. Very good. Plate tectonics, divergence, good. See, understand on the western side, there is compressional force. You had your Nazca. See, Nazca is here. Your Nazca plate was coming and colliding with South American plate. See, once there is compression, naturally can't have wider shelf. If the shelf region is there, slowly the shelf region will become smaller and smaller. That is why it is very, very narrow. Here, there is no compression at all. Even if divergence is there, divergence is very far away. And divergence one way or the other is not going to affect your South American region. That is why wider and narrower. Always remember, when compressional forces or conversion margin is there, your shelf width will reduce. Common sense. You compress, you reduce the width. Ready? You just take that here. Draw a simple diagram. This is not needed. Take South America. Wider shelf on the eastern side. Very narrow. Why? Because of convergence. Convergence makes it narrow. And on the eastern side there is no disturbance. So here there is divergence. Draw a small diagram. I've drawn it bigger, but a smaller one would do. Good. Very good. Like I think 4 people have guessed it correctly. Good work. Really nice that in spite of work you're learning. That is quite an achievement. Weekend batch, really good work. Other batches, you don't know, you think I'm scolding you, you should look at me in the other batches. They make one error, I get very angry because you're learning full time. The GSPCM weekday batches, weekend batch, you're working and learning. So when you answer something correctly, I'm really happy. Honestly, because I know how difficult it is to study after working. It's so horrible. Very, very horrible. Second is continental slope. Okay. See, slope section, as the name states, it is when it becomes much steeper. Okay. Continental slope proceeds to have a steep angle, from shelf break. It is known for submarine canyons. I'll draw the diagram. Then we need to discuss one concept called abrasion. Shelf slope. The break point is called shelf break. That's all. This is called a shelf break. Exactly where the dipping is starting. No? Shelf break. And these are submarine canyons. Submarine canyons. So now we need to address the word. Shelf break is fine. That's where the slope is becoming steeper. We need to understand this word, submarine canyon. So first I'll need to teach you what exactly is a canyon. Before that, we'll need to understand what is a valley. So that's why I told you some concepts will need to be revised or introduced before we understand submarine canyons. Ready? I'll read it one more time, then I'll flip over to the next page. Continental slope proceeds to have a steep angle from shelf break. It is known for submarine canyons. So what we'll understand is, what is submarine canyons? How do submarine canyons get created? Because the next step, called as continental rise, is related to submarine canyons. That's why. So first we'll understand what is a valley. See, valley is any negative landform. Valley is the most simplest of terms, but every textbook will give you different definitions. Just understand it's a negative landform, a depressional landform. It's depressed compared to the surrounding region. Usually it is created by a river. Usually a river flows through. This is a valley. Don't think it's too complex. Every time 5th standard or 6th standard, when your drawing teacher asks you to draw scenery, this is what you would have drawn. Correct? I can put a sun here, but it will become political. But when you drew, you might have drawn. Okay. This is your valley, this particular landform, which you find right there. This landform is your valley. Okay, you call it as V-shaped valley. At the start of the river, you'll get V-shaped valley because the depth component will be more. The river will have more energy to erode the depth. The V-shaped valley. Valley. Number 2. What do you mean by gorge? Okay. Very, very steep valleys are called as gorges. Very steep. You might be thinking, well, the same thing is done here also. Not technically. See, a valley can be gentle also. This can be a valley. You can have a valley like this, no problem. A very steeply shaped valley is a gorge. Steep valley. Steep valley is a gorge. We will see pictures for clarity. A lengthy gorge is called as a canyon. So a gorge which extends for maybe at least hundreds of meters. Lengthy gorge is called a canyon. Canyon. Usually these are sculpted by rivers over land. Valley is a negative landform or depressed landform. Gorge is a steep valley. How? See, thing is, valley can be gentle steep. If it is very steep, it's called a gorge. Lengthy gorge is a canyon. Use the word finish if you're ready. Good. Fine. I'll show you a picture to get the idea of canyon clear. Oh, sorry. I should have looked at there. Slide exhaustion. Just one picture. See, because if you want to know what is submarine canyon, first you should need to know how do canyons look like on land, isn't it? River Colorado. Do you remember by any chance? River Colorado, United States of America. We introduced that during map reading session. Wow. You might have photoshopped. I'm pretty sure they photoshopped this. Yeah, but still. This is a canyon. Look at the valley. It's very steep. Right? Very steep. See, you fall from here, you're dead for sure. Maybe you can remember like that. You push your friend inside a valley, not necessary that your friend will die. Push him inside a gorge, confirm death. I'm very happy. Now, this gorge is very lengthy, travels for hundreds of meters. Okay, so you can see the river. Okay, the river flows through. So it's quite long. It meanders when it goes on for hundreds of meters. Okay, even kilometers altogether. So a lengthy gorge is called as a canyon. Now I think the word canyon is fine. This is a canyon. Okay, a lengthy gorge moving over a long distance. Now we will come to submarine canyons. Submarine, which means this structure, which you find right here, if it is found underwater, it is called a submarine canyon. And surprisingly, submarine canyons are present over continental slope portion. The structure which you saw right there, okay, is actually found right here over your continental slope. So it's really perplexing. Why? See, rivers on land will have the capacity, will have the erosional capacity to create canyons. Perfectly fine. So how are they created underwater? That's a question mark. Right? So for that, we need to understand a method of erosion by rivers. That's called as abrasion. Once abrasion is introduced, we'll introduce turbidity currents. See, if this is, I think you see the side. Let's say this is the river bank, the limit in which the river flows. If a rock is sticking like this, just by the velocity of the river can take this off. This is one simple method of erosion. Very simple method. Just by velocity. It is called hydraulic action. The terms you need not write, just for reference. Called hydraulic action. One more way I can try to erode things is I can solute, you can create solution. Maybe I can dissolve the chemical and then try to break apart. Third method, I've already eroded this rock. I've eroded this rock. Now this rock is going to hit the river bank. When I move, I push it, hits the river bank. Once it goes and hits the river bank, naturally the soil will break down. So some soil will break, then after that I will erode. So what I've done is, I have not just used my velocity, but I'm using tools for erosion. A rock which is already existing, I take this rock, throw it here. Once I throw it here, this will hit here, this will break. As it breaks, the eroded sediments also, I take it up with them. That is called as abrasion method. Abrasion is done by everyone. Wind does abrasion, glacier does abrasion, running water also does abrasion. So abrasion is a method of erosion. Again, abrasion is a method of erosion where tools are employed by the agent. Tools are employed by the agent. Okay, the agent can be water, wind, etc. Abrasion. It's like you throw a stone in one area and the glass breaks. Then you collect the glass and run away. I think that example was much easier. Take stone, break glass, take glass and run away. Use the word finish if you're ready. Submarine canyons same as trench. No. Trenches are different. Please wait for trenches. Trenches we will see. Just a few more slides. We finish this, then we are done. Later, after research, they understood that submarine canyons are created by turbidity currents. I will give the definition, just one line. Turbidity currents, which technically erode submarine canyons through abrasion. See, the shelf portion which you find here is technically part of continent. So even if this is 100 kilometers, you will find the particles which are eroded from the continent settling here, right? I mean, deposited here. So this will find some stones will be there, angular fragments, gravel, all those elements will be there. Now, you take the top surface of water, the top surface of water can have severe agitations. For example, I can agitate the top surface by having a cyclone here. Think about it. If you have a very severe cyclone, naturally the water will oscillate. Or you can have a severe earthquake. If it's a convergent margin, yes, you will have earthquakes. Earthquakes will create oscillations. At the same time, very powerful waves. Waves can create oscillations. So there are several methods through which the water can get oscillated above the continental shelf. Now, when they get oscillated, it's like stirring up. See, have you ever tried this where, any mug or any tumbler which you're talking about, there is some sediments, you just try to stir it up, all your sediments get disturbed. Feel that? So when you disturb the sediments through any of the above processes, that is a cyclone or very powerful waves or earthquakes, water will try to stir up and then it will descend down. Okay, it's like pushing water from the top. When it descends down, it will collect sediments. So I need to get tools, isn't it? Tools are very important. These tools come from continental shelf. After taking tools, I throw it in the submarine, I throw it in the continental slopes. I take the stone, I throw it on the windows. After throwing it on the windows, I create submarine canyons. As simple as that. Now I think the example is okay. So let me write there, turbidity currents or underwater avalanches, avalanche, which is of muddy water, which erode submarine canyons, through abrasion. Full stop. Abrasion. So the eroding materials are contributed by shelf and erosion is done on the slope. So if this is done, the next three are very simple. If you are ready. Right, thank you. See, point 3 is simple. I'll draw the diagram here itself. See, whenever there is erosion, there will be deposition. So at the end of the slope, there will be deposition. Once you deposit your sediments, naturally there will be an increased elevation. Not talking about high elevation, but compared to my slope section, we'll definitely have some sort of rise. This is continental rise. And why is continental rise formed? Because of deposition. That's all. That's number 3. Way too simple. Continental rise is formed by the deposition of sediments from the slope. Number 4, abyssal plain is the deep ocean plain. Deep ocean plain it has an average depth of 4.5 to 6 kilometers. This is a deep ocean basin. Okay, abyssal plain. Just a word on terminology here, very simple. History you'd have learned, no? Himsa means violence. Ahimsa is non-violence. Baisal means bottom. Baisal means bottom. Abaisal means, most people will tell me top 9. No bottom, it's very deep. That is the meaning. Abaisal means no bottom, very deep plain. Okay, 4.5 to 6 kilometers. Now we will understand trenches, because this 4 segments you will find along or towards a passive ocean margin. Passive ocean margin is, close to a divergent margin you'll find these. Trenches will be found during convergent plate margin, because due to compression, you'll completely destroy this 4-part structure. You ready for this? I'll repeat the 2 statements and I'm flipping over, okay? Because only 2 lines. Continental rise is formed by the deposition of sediments from the slope. Abyssal plain is a deep ocean plain. It has an average depth of 4.5 to 6 kilometers. Here we are. So 1, 2, 3, and then 4 maybe. This you will find in a divergent plate margin, towards a divergent plate margin. So all the components are retained. 4. No issues. Now what you have convergence on the other side, that is when trenches are formed. There was a question, isn't it? I think someone asked, where trenches are formed. This is a trench. Continental slope is here. Due to compression, you'll find a very steep fall. This is the trench along convergent plate margin, the deep V-shaped structure. You'll go deeper and deeper, possibly 5 kilometers, 6 kilometers, 9, 10, and even 11, Mariana Trench. So there is no concept of continental rise here, because all the sediments moving up down from the shelf section will eventually go to the deep water. There is no point you'll build the shelf. So towards convergent margins, you'll find trenches. This is why Mariana Trench, Philippines is there in the convergent plate margin. That is where you'll find trenches. You won't find several trenches in the Atlantic Ocean, because Atlantic is a divergent plate margin. Able to make the connection. Even if there are trenches in Atlantic Ocean, next time you look at the map and see, trenches will be close to Caribbean Sea, the Tonga, around the Caribbean, because Caribbean is a convergent plate margin. Caribbean is convergent with North America and South America. Apart from that, Atlantic is pretty much nil. Okay. I need to finish it with one minor landform. I use the word finished if you're ready. After that, we will start with salinity. I'll give you the basics, then we'll close. Right, minor landform. See, the most abundant landscape, the most abundant landform which you'll find underwater are seamounts. Okay. Seamounts are the most common landforms of the ocean floor. Flat top seamounts are a result of wave erosion. And are called guyots. G-U-Y-O-T-S, guyots. So this is technically my seamount. If the seamount becomes flat, then you call it as a guyot. That's all. That's it. So who gave haircut? Waves. Waves can erode this section. Any possibility that trenches formed in the divergent boundary or only in convergent boundary? Akhilesh, no doubts at all. You find a trench, it will be a convergent margin, because there is no possibility you can get trenches in divergent, because you need deep structures. That is possible only under compression. Divergence, there is volcanic eruptions, no? So naturally, they'll only fill up the land area. You can't have deep structures. So if it's a statement question, if they ask you, you can be very sure. Convergence, trenches, that's all. I think you know how seamounts are formed. Volcanic eruptions, that's all. consistent volcanic eruption, divergence, you'll pour out lava on either side, accumulation, igneous rock, seamount. Okay, it'll have a funnel, of course, which is connecting to the bottom surface. See, we can't look at salinity in detail, but we have at least 8 minutes to 7:20. So two concepts alone I'll teach you. The definition of salinity, water salinity, and why is seawater saline. We'll address those 2 points, then I'll take doubts, okay? First, the definition of ocean salinity. See, stay back. These 8 minutes will be crucial because I'm going to explain why seawater is saline. Don't leave. Ocean salinity is a measurement of dissolved components and does not include particles in suspension. Full stop. Measurement of dissolved components and does not include particles in suspension. See, understand this word, what do you mean by dissolve right here? Whenever someone says dissolved, you're talking about completely destroying the structure. You're talking about chemical interaction. Chemical. That is, you drop sodium chloride in a beaker of water. Sodium chloride, you start stirring, sodium chloride will simply disappear. Not going to see that. That is dissolution. Meaning makes sense. So when you say particles in suspension, like we're talking about sand particles here, clay particles here. Clay particles are not going to get dissolved as such. You don't calculate them when you study salinity. You're focused on what is chemically inside. Okay, like it should technically disappear. That is dissolution. Meaning makes sense. Now, within this, we have different levels of measurement, but currently we have a common mode of measurement. Like how do you exactly define it is by something called as parts per thousand or PPT. Like the average seawater salinity is 3.5%. 3.5% meaning for 100 parts of any volume of water, you will get 3.5 parts to be salt content. Right there. The average ocean salinity is 3.5% expressed as 35 parts per thousand PPT. See, please don't ask me how it is done. 3.5 is for 100. You multiply and divide by 10, that's all. You get 35 by 1000. Is it fine? 35 parts per thousand. Suspension means carried. See, for example, road dust is carried by air or road dust is suspended in air, right? So, water will naturally carry several particles. That is meant by suspension. I am suspended in the air when the lift fell down. I will die, of course, but still. That is suspension. Okay. So understanding this point is very simple. If you remember the climatology concept also, you would have heard these things in newspaper. ppm. ppm stands for parts per million. ppb stands for parts per billion. These two calculations are used for atmospheric measurements. You want to measure something like carbon dioxide, which is quite abundant compared to the others, use parts per million. If you go for an atmospheric gas, which is quite recent or has a less composition, you go for ppb. ppb is parts per billion. Okay, example, nitrous oxide, sulfur hexafluoride. Get the idea? So those are measured in ppm, ppb. When it comes to ocean salinity, it is ppt. Now the last part for today. Reason for seawater salinity. Paradox. You know what a paradox is, isn't it? A statement which contradicts itself. Rivers are fresh water. That is the reason we use them for drinking purposes. But actually, It is the same rivers which made the ocean saline. Paradox. So how exactly does it happen? See, there is a concept called residence time. Residence time is how far a particular salt element is going to stay in that water body. Let's take Kaveri River. Southwest monsoon provides peak rainfall during the months of June, July, August, and parts of September. So when there is increase in volume of water, Kaveri River will erode well. You increase volume, there is more volume naturally. So when there is erosion, what Kaveri is naturally doing is taking large amount of minerals. Okay, but listen carefully. The mineral content which is there in Kaveri River is very, very less. See, minerals, you're saying minerals is nothing but salt. I'm talking about sodium chloride, calcium sulfate, aluminum chloride, which you'll naturally find in the earth's crust. Okay. Now, this mineral content will be very, very less. Always remember, it is less. That is why you drink Kaveri water. That is why you drink Ganga water. No problem. If it is polluted, of course, but you get the idea. Now, when the water meets the sea, in one instant, if you take, there will be large amount of fresh water which is getting added. Only small amount of salt. Yes, because salt content is less, it's fresh water. Very less amount of salt. But once you add salt inside the oceans, unlike the rivers, there is no way to discharge. River is constantly discharging. That is why salt doesn't accumulate. Okay, like rainy season is there, erosion, put the salt out. Erosion, put the salt out. Ocean, it's not that salt won't get removed at all, but processes are not very dominant. I'll tell you when will salt get removed. Several organisms are there in the ocean floor. You'll take coral reefs. Coral reefs need calcium carbonate cells. Is it not so? Which means you need calcium carbonate shells again. Any marine organisms need those shells, which is technically on their back. They will derive salt from the oceans. That's one method where salt removal is there. Second one, you can talk about human beings. Human beings do remove salt, but the percentage is way too less. One more method is sea spray. Sea spray is when there is constant lapping of waves on the shore. Some amount of salt is thrown over back to the landmass again. And let's say there is a conversion plate and the ocean plate is sliding inside the asthenosphere. Definitely some salt will get removed. But all these processes are, even if they act at global level, are not quite as powerful as removing salt, removing considerable amount of salt. So if you take a salt particle and drop it into the ocean, it will stay there for quite some time. When I say quite some time, at least 1,000,000 years. That is the problem. The oceans became saline. Okay, so salinity was actually added by rivers primarily because the residence time of a salt molecule in ocean water is way, way higher. I'll write that paragraph. So once that is done, the class is over. If doubts are there, you can stay back. Okay. When rivers meet the sea, they add a large volume of fresh water, and a small percentage of salt. But the salt has a higher residence time, and accumulates, making the sea water saline, or making the oceans saline. So that's it for today's session. 2 more sessions and we're going to wrap up oceanography. And please remember, this topic is way too crucial. Okay, usually you have this integrated, the subsections also, but lack of time, that's the reason. So next class will continue from here. And possibly next class itself, I'll try to finish El Nino and La Nina. Okay, that will give more priority. Okay, so if any doubts are there, please go for hand raise option. Others can leave. Fine, thank you. So I'll wait for doubts. Go for hand raise. It will better clarify it through audio. Slides, don't worry. Slides anyway, I'm going to send it through Telegram. I'll send the coordinator. She will send it to Telegram. Okay.
Hello, sir.
Hello, yes.
Sir, you said the salt is dissolving the seawater, so that salt content is high amount in the water.
Yeah.
Sir, my question is, in river salt content is low, sir, and
Yes.
across the river we construct dams, sir. So
Okay.
salt will sediment and deposit in that same place. Only after few months, only after 1 year after only we release the water, and just only water, and that salt is mixed with water. Sand, mud also. So how it will increase the salt content in the seawater, sir?
See, you're asking about whether dam construction is going to affect, whether dam construction will result in more salt content in the rivers. That's the question you're asking.
Will reduce the salt content, sir,
See,
because
hold on a second. Hold on a second. Please wait. Please wait. Let me finish the statement. Then I think that will answer your query. I think the number of rivers in the world is quite incalculable. Say rivers, we're not talking about river systems as such, small rills, runners, and all that. And even if human beings have started constructing dams, we haven't blocked every source of water. So our impact is still less in that count. Is it clear?
okay, sir.
There are so many rivers.
Hello.
It's not that we have dams everywhere. Is it okay?
Okay, sir.
Hello?
Hello, sir. Is it audible?
Yeah, it's audible. Go ahead. Did you get the point I made?
Yes, sir. Yes, sir. And one more query, sir. One more suggestion, sir. So the evaporation rate will be higher in seawater, sir. That also will be one of the reason to increase the.
See, yes, you're right.
Salt content.
Evaporation will increase salinity, but there are five factors which affect salinity. That is the next section which we usually deal with. I'll tell you the five factors. Like that will be the continuation of the class anyway. Evaporation will affect salinity. Rainfall will affect salinity. Glacial melting will affect it. Glacial formation will affect it. And at the same time, whether the sea is close to a river or the sea is whether you're in shallow water or whether you're far away into deep sea, that will also affect salinity. So five major factors are there. Okay. Evaporation is right.
Sure, sir. And one more query, sir.
Sure.
Hello.
Yes.
Sir, in my nearby places, sir.
Okay.
In one mountain, sir, in the middle of mountain, there was a natural blast, sir. What is the reason behind it, sir?
In the middle of mountain, there was?
Middle of mountain, yes, sir. Middle of mountain.
There was a blast.
Sudden blast. When I was saying, sir, I heard about this incident.
Where are you from? I mean, which place are you talking about?
In Dharmapuri district, Tirthamalai.
Okay. Wait. See, this
in,
I can only
nearby
judge.
2002 thing.
Okay, see, this, thing is, the only one connection I can give you, but I do not know the intensity of the blast or how big it was, but I can tell you what happens in a semi-arid condition. See, Dharmapuri is in the rain shadow region of Tamil Nadu. So, rainfall is relatively 50 centimeters approximately. Rarely it will exceed 60. It's technically dry land. So, in dry land conditions, rocks have one issue. So, if you have very high temperatures for a long time, and let's say for that particular rock, you do not have any precipitation for 1 year or 2 years, it is not exposed to water at all. So all of a sudden, if there is increase in rainfall, okay, that will meddle with the expansion and contraction of the rock. In that case, you will get explosion. So this will happen under severe, like close to 2 years, let's say you don't have any rain at all. And all of a sudden there is sudden rain. All of a sudden there is sudden rain. That's twice repeat. All of a sudden there is rainfall. It affects expansion and contraction of the rock. So immediately there is blasting. Okay, this is observed in deserts usually, but Dharmapuri is quite 50 centimeters, not an arid land. So this is the only explanation I can give you. This is something which happens in deserts for sure.
Okay, sir.
Okay. Thank you.
Good evening, sir.
Yes, ma'am.
Sir, regarding this methods of salt removal, can you please elaborate the point, sir? I heard coral reef, salt manufactured by
marine organisms. Organisms can remove when they form shells. Number 2 was human activity. Humans are removing salt for industrial purpose. For industrial purposes, we do. Number 3 is called sea spray. Sea spray is waves coming back to land. Sea spray. When waves lap against the shore. When, like, every time it happens, every beach, when waves come to shore, some amount of salt is thrown back. Last one is subduction into asthenosphere. So once you go inside asthenosphere, you will definitely remove salt. Subduction. This is 4 points.
Thank you, sir. And one more doubt, sir.
Sure.
Can you explain about Salt Lake and Dead Sea, sir? Is there anything special about the salinity over there?
And the point is, Dead Sea is a desert actually. So you know that in a desert condition, if it's a very narrow lake, there will be too much of evaporation. So consistent evaporation has made the lake very saline. So it's more to do with the climatic factor actually. Okay?
Okay, sir. Okay, sir. And regarding Salt Lake, sir? Salt Lake.
You take any salt lake, for example, it will be there in the arid region. I'll give you one more example in Rajasthan. There is Lake Sambar Salt. Or Sambar Salt, should I say. Sambar Salt is the largest saline lake in India. So it is in a desert region. So desert region, consistency and evaporation. So based on where my lake is located, the amount of salinity will change. Is it fine?
Yes, sir. Clear, sir. Thank you.
I will send slides. I'll send it to the coordinator. You'll get it through Telegram. So you won't miss anything. You don't worry on that. Because every slide, not necessary. You won't miss anything. Hello?
Hello, sir. Can you hear me?
Yeah, go ahead.
Yeah, hi. Little doubt I have. So you are saying that the trenches is forming because of convergent forces, right?
Yeah.
So I saw in the trenches there in the middle of Arctic, the area, Pacific Ocean. But there is a divergent thing only, right? How it will come?
Where exactly? Middle of?
Mariana Trench.
Mariana Trench is not divergence, it's convergence. Where is Mariana Trench? Which ocean? Check your atlas again. Which country?
Pacific.
Yeah,
Ocean,
Pacific
right?
is convergence. This ring of fire. Everywhere there is convergence. Is it near Philippines or not?
Yeah, it is there near to Philippines.
Yeah, Philippines plate colliding with Pacific. It's a convergent margin.
Okay. So, and one more doubt here. So we have that slope, right? And the sub shell we have because of some wind, some happen. It is sloping that soil something is slanting over to the ocean, right? That will affect in this continent. How? What is the effect? It will be because ocean is big, right?
I missed that part. There was slight interruption in audio. I understood till that there is submarine canyons in continental slope. After that, I missed the question. Just come for that last segment of the question now.
That it is leading to the continent uprising, right? Ocean floor uprising. So it will have any effect.
No. This is not ocean
floor will rise actually.
Again. The point is this: it's not ocean floor rise. Look at the width I've drawn. Actually, it's a very small area compared to the deep oceans. Okay, it's not going to lead to high elevation and all. Locally, it will rise. That's it. And even this rise is possibly few hundred meters, not more than that. It's very local. Okay, you can see the size difference. Small region. Is it fine?
Okay, thank you. Okay.
Hello, sir, can you hear me?
Yeah, go ahead.
Sir, actually, today there's an article on the tropical cyclones moving closer to the land.
Exactly, I saw it.
So do we need to focus on these type of articles
See,
when
Nishit,
it pops up?
in the entire article, there's only one point you need to note down. There was a data given. If I'm not wrong, this is what it was given. Uh, since 1970 to 2000, every single year there were at least 2 cyclones which moved inland. Something like there was a number. Take
Yes.
that one line. That one line is enough. That's all. Beyond that, there is nothing in the article you can use for exam. Like
Okay.
I'll tell you where all to use it. Let's say there is a question on cyclone. In the conclusion part, you can use. There is a question on impact of climate change. You can use that point. General Studies 3, they're talking about disaster management, or there's a question on disaster. You can use that. So you can take that point. You can fix it anywhere, like anywhere as it is relevant. This is why you read newspapers. Good point. Like you take that number only on that day, that article will come. So you steal that point and keep it with you. Use it appropriately.
Okay, great. Thank you.
Yeah, sure.
Good evening, sir. Am I audible?
Yes, go ahead. Go ahead.
Sir, I couldn't understand the part, the relation between the submarine cannons and the turbidity currents. I didn't understand it properly. Sir.
Hold on.
Explain it again.
You understand abrasion?
Yes, sir. I understood abrasion.
Abrasion is fine, isn't it? This is fine.
Yes, sir.
The thing is, you understood that the water can get agitated by cyclones and earthquakes. This section is okay.
Okay, sir.
This is fine. See, if those two are fine, then this should be quite easy. See, when a river flows, if it is already having rock particles, this rock particle will be forced onto the river bank. This will break open. A rock is there, this rock is forced onto the river bank. So this river bank will break open and there will be more erosion. That is how rivers either widen, or I can take the rock, this rock can collide with the bottom also. This will become more deep. Natural for fluid systems erode. That is what is happening. When water descends down from the top, it is going to break open the submarine canyon through erosion. Now is it clear?
So the submarine cannons are already present in slope.
No. I'm telling the reason why they are present. Turbidity currents are the ones which you create. Actually, it was like this at the start. This became this.
Okay, sir. By the deposition, submarine cannons are created.
No. Erosion. Erosion submarine canyons are created. Deposition is here. I erode here, I deposit here. Okay.
Okay, sir. Got it. I got it. Thank you.
Sure.
Hello.
Hello? Yes?
Yeah. Good evening, sir. So,
Yes,
so
yes.
you told about this expansion in this fault block mountains, no, sir.
Yeah. Okay.
So out there, wouldn't it be similar to the volcano divergence margin? So wherein wouldn't there be any volcano eruption or something? Because as
Definitely. You're right. You're totally right. There will be. See,
so what are
let me
the
tell you,
main-
let me draw the diagram for how things will look like in a volcano in a mid-Atlantic ridge. Okay. Hold on a second. Let me just draw the diagram and your doubt will be cleared. Let's say you're in the middle of Atlantic Ocean. This is how we form a seamount and you get fault block mountains too. See, due to several volcanic eruptions, the basaltic rocks are formed. They become mountains like these. Is it clear? This is how things get accumulated. They become mountains. Now, what happens is the longitudinal structure will be this. This is my seamount. Now, for the next volcanic eruption, this will slowly get melted, eroded, formed. This will still get depressed. Again, there will be an eruption. This rock structure will get integrated again. Now, you're able to understand what happens?
Okay, so if my understanding is right, so fault block mountains are part of volcano mountains, right?
Yes, yes, you will find volcanoes there also, but volcanoes are not very explosive. They're effusive volcanoes, flowing volcanoes.
Okay, sir. Thank you, sir.
See, I think Ashwin, your question on seamount is clear, man. This is how seamount got formed. Okay, very simple, man. Like accumulation, that's all. Accumulation of lava. Lava becomes basaltic rocks. Subduction. Subduction is this ocean plate subducting until continental plate. That's subduction. Still, we didn't get missed slice of Mediterranean climate. Okay, I'll take from some other batch and send it to you. 2009716. And that's the last one. Is there anything else? Mount Everest is increasing height. Recently, revised height was given. Yes, man, it's a conversion margin. India is still pushing towards Eurasia. So, Everest will continue to increase. Right, that's the last one. Fine then. So, we'll close the session and save the slides. Take care. Hopefully, see you next weekend. If I get 2 sessions, 5 to 7:30, 5 to 7:30, 2 days, we are wrapping up geography, world geography. Bye for now.